That look good.
Yeah, that look good.
TI Sports, it's in the watch.
Welcome and thank you for watching. Today we're going to go over the Kronos watch made by Texas Instruments. Inside it has an MSP430 microcontroller. Before we get started, we're going to go over what exactly the Kronos watch already does. It's a normal featuring sports watch with accelerometers, altimeter, and heart rate monitor. But the main thing we're worried about here is the accelerometer and using that with our added on application, the Swing Analyzer. But before we get into that, we're going to go over group bio and why we picked this and the big business behind it.
Alright, to do a little group bio, our group consists of 3 University of Cincinnati students. Brandon Bright, electrical engineering undergrad, graduating in 2012. Mark Lobato, computer engineering undergrad, graduating in 2013. And Matt Skinner, electrical engineering undergrad and master's, graduating in 2012. Alright, now that you've learned a little bit more background about our group, let's go into the design and business plan. We wanted to mix our innovative design with a marketable product to start a new business for Texas Instruments. And our theme was going from behind the scenes to center stage. Because what do we mean by that? Our company is majorly invested in the insides of electrical and automotive through industrial and computer devices. We wanted to expand this using the TI Kronos watch and our application. For instance, big name companies like IBM, Intel have started new ad campaigns to help remind people that they're on top of the electronics market because most of their parts, for instance, like ours, let's look at the product inside breakdown from computers and all types. We've got 96% invested in communication, computing, industrial, consumer electronics, and automotive, and only a small 4% invested in education. But what does the world see us as? 99% education and calculators, and 1% computer chips. This is important because we need to remind society that we are on top of the electronics market, whether it be from communications and computing to industrial and consumer electronics. So when new companies start and they're looking for anything from an analog, embedded processor, or a wireless device, our name is the first thing that comes to mind for them. And why else is this important? University relations. We want to get these parts, microcontrollers, into classes and senior projects early in the student's career, so that when they come out, they know that our parts are the best and that they're used to using our parts. So when they go to make new business, they bring our parts with them. And where does the Swing Analyzer fit into all of this? The Swing Analyzer application, paired with the TI Kronos watch, shows that the chip can be used for an innovative design and be a marketable product. What else does it do? It spreads the word to the consumer through sports and fitness and innovation, which those two, sports and fitness together, are about a $12 billion industry. So if we can utilize those industries along with TI's watch, we can really spread the word. And what all does this do? It builds interest in the possibilities of the microcontrollers that TI offers. Alright, now that you have a good background on why we picked the Swing Analyzer as our application, we're going to go into the graphical interface made in LabVIEW. And what we're going to show you in the graphical interface is how we use LabVIEW to take the data from the watch and the accelerometers to transpose that into swing data and show you how we compare speeds, position, and club face angle to help the golfer have better swing overall. So I'm going to give it over to Mark Lobato and let him explain.
Thanks, Brandon. As he mentioned, I will be the one to show you our program. So when you open the program, you see what you see here. You have a sync button, an ideal button, a compare button, a stop execution button, and a tab interface that has acceleration, position, speed, club face angle, and save. When you're ready to use the program, you click the sync button. After this, it tells you to initiate the connection by pressing the down arrow. So what you do is you go over, get ready to swing the golf club, then click the down arrow on the watch. When you do that, it starts collecting data. So the watch is transmitting the acceleration values to the computer, and it tells you that. So what you do is when you're done with your swing, I'm just kind of idling swinging the watch around just to show you something. You click the down arrow again to end the transmission. And when you do that, it will kick you out and start analyzing the data. But it shows you the acceleration in the z-axis, the y-axis, and the x-axis with respect to time. So that is the acceleration tab. Next, we have the position tab. This shows you the front view and the side view of your swing. In the front view, you would see a C shape based on the position of the golf club during your swing. And from the front view, it should be a C shape. The side view, it should be a plane, and according to the golf community and our research, a good swing, a good solid golf swing, follows it. Your arms follow a plane when looked at from the side. In the next tab, we have the club head speed. So this shows you the speed with respect to time as to how fast it's going. So it should go something like a little parabola up on your backswing, then back down, and then really fast as you're swinging it and hitting the golf club, and then it would go back to 0 after you hit the golf ball. Next, we have the club face angle tab. This compares the club face angle difference between your current swing and your ideal swing. Generally, the ideal swing would be your 0-degree line, so you're calculating the difference between the two. So throughout the swing, you can tell if you're twisting your arms in a wrong direction, that maybe makes your swing a little awkward. And then at the bottom, we have the angle at which you make contact. So if you hit it with a positive angle, it's going to most likely slice or go wide. And then if you hit it with a negative angle, you're going to pull it the other direction. After that, we have the Save tab. This is where you select the file path that you want to save all the data. This is pretty much just the Z, the X, the Y, and the button data. So next we have the Ideal button. This saves your current swing as the ideal swing. So if you save it as the ideal swing, you can then compare it to another swing later. Say the swing you just made was really good, you want to save it. So you click Ideal. Then the next swing, you really didn't do so well, you know you sliced the ball or you just really felt that it was wrong. You can click the Compare button. This would compare your current swing against the ideal swing that you just saved, and you would show you in the position, speed, and club face angle tabs how far you were off from that swing. So you could actually see, that's the whole point of this program, is to see what you're doing wrong rather than having a coach tell you or just doing it by trial and error in a driving range and spending untold amounts of money just sitting there swinging at balls for hours on end. This really just shows you what you're doing wrong, and you can really focus on correcting it. Now that you see how to use our program, I'm going to let Matt Skinner take over and explain to you the physics and mechanics behind golf swing analysis.
Thanks, Mark. So once we have the data being outputted, we brought it into Excel so we could use some physics equations on it and calculate speed, height, and some other parameters to fully analyze the golfer's swing. Our first attempt at this had us taking the average acceleration over every 50 millisecond interval and integrating this twice to get velocity and position values. Now this should work in theory, but in our case the accelerometers have gravity also calculated in the data, which means even if you weren't moving the watch, that gravitational value would be integrated to show a changing velocity and position that really wasn't occurring. And also, with no gyroscopes on the watch, it's really hard to tell if it's radial or linear acceleration. To solve this second problem, we thought we could implement the altimeter to show a changing height of the golfer's swing from the bottom to the top. However, this proved too difficult to program because you have to program it on the watch, and the acceleration mode didn't cooperate by letting us output the altimeter data. So we called VTI Technologies, who manufactures the accelerometer, and they said that there's a DC and AC component to the signal being outputted. The DC component is the one that represents the gravitational data, while the AC was the one that was measuring movement. So we had to use some sort of filter to separate those two. But we thought about it, and we could use the DC component to find the watch's orientation and more accurately calculate where it is and where it is moving to with the velocity vector of the AC component. And here's an example of our data sheets. As you can see here, this is just the x-axis data, and we converted it to the proper meters per second squared, and we used 2 low-pass filters to get the DC component removed, and now you can see the AC component, which is just the moving acceleration. And then if you subtract that from the original data, you would have the DC component, and we could, as I said before, use that to orient yourself with the X, Y, and Z component of gravity. Now, we took the orientation and movement acceleration to calculate the upwards acceleration in each X, Y, and Z components, and from that we calculated the overall upwards acceleration, which we plotted here in the upper left. Now this value is always positive, so anytime that the acceleration reaches 0, we assume that to be a sign change, and that's where we get this upper right graph with positive and negative acceleration. For instance, at the top of a golfer's swing or any change in position like that, there's clearly a change in the acceleration. And if you take this and integrate it, you will get velocity, and integrate it again, you'll get position. So here you can see the upswing, his downswing, and then his follow through. Now, there were only 8 data points or so for the actual swing itself due to the 50 millisecond intervals. So one of the things that we would like to do further is increase the frequency of the data rate so that we can get cleaner data, because the noise that you see up here in the acceleration doesn't look too bad there, but integrated twice becomes larger and larger error. And also we'd like to implement the altimeter just to be a 4th data set and enhance the overall quality of the data we're getting, so that hopefully our end result will be a full front-on view of the golfer's swing.
Thanks, Matt. Thank you guys for watching. I hope you enjoyed our presentation on the Pro Swing Analyzer. To learn more information, you can go to our wiki page and look at our detailed business plan and more pictures on our application. Thanks again for watching, and don't forget to vote for us on InfoLink.
Man, I love college. Do I really have to graduate, or can I just stay here for the rest of my life?
TI Sports, it's in the watch.